Hello, this is video 63, and we're going to start our discussion of static equilibrium. So, the definition of static equilibrium is that your object is going to be motionless or at rest. You can see it in this picture. This person is balancing the bike, and he or she is at rest. So, in order to be in static equilibrium, there are two conditions that must be met. The first condition is that the net force must be zero in each direction. So the sum of the forces in the x direction must be zero, and the sum of the forces in the y direction must be zero. These are the same conditions that we saw in the past in chapter 4 when we were doing Newton's second law problems, and there was no acceleration. So this is necessary in order for the object to be at rest. Let's do an example testing this first condition for equilibrium. A sign is hung from a uniform horizontal bar as shown. What is the direction of the x component of the force exerted on the bar by the wall? And we're going to see this image again. I just wanted to bring it up here so we can start on it, kind of analyze what's going on here. Imagine this is a wall over here. There's a bar, horizontal. There is a cable here. This is a cable right here. And then there's a mass, like a sign, being hung here. So, what's the direction of the force exerted on the bar by the wall? So we know over here that there's some kind of force exerted by the wall on the bar. And we don't know if it's going this way or this way, but this problem is asking us about the direction of the x components. So we actually already know that, well, it's going to go to the right because we know that a wall exerts a normal force on any object, and that's going to be away from the wall. So we already know it's to the right. But the purpose of this problem is to apply that first condition of equilibrium. Let's say we didn't know which way the force was, but we knew that in the cable here, that cable, that tension always points away from the object being this bar here. That's what we're looking at. So that means that the tension has a component in the x direction to the left, right? It has a component this way. So the sum of the forces in the x direction being equal to 0 tells us that if there's a force to the left here, then there must be a force to the right here to balance it out, since this bar is not moving. So I'm just showing you this, even though you already knew the answer, I'm just showing you how to apply these conditions so that we'll be able to apply them to more complicated problems. Let's look at the second condition for equilibrium. So this is the new one. And it says that the net torque must also be 0 for your object to be in static equilibrium. So this is to prevent any kind of rotation. So let's take a look at an example for this one. So this one, same picture again. What's the direction of the tension exerted on the bar by the cable? So again, we already know that the tension is going to be away from the object, so it would be more an upward rather than a downward direction. But in order to see how we can apply this condition of static equilibrium, so if we pick the pivot point to be right here, now we're going to learn in the next video that we can pick the pivot point to be wherever we want to. But if the pivot point is here, then we know that the sign here exerts a downward force on the bar. So that means that the sign causes a rotation that is clockwise. So if the net torque must be equal to 0, that means that the torques must balance. If there's a negative torque clockwise, that was the sign convention that we used, clockwise rotation is negative, then there must be a positive torque to balance it out, a counterclockwise torque. So that tells us that the tension must point in this direction away from the object and upward. So I'm just showing you how this works, this condition for static equilibrium, what this really means is that the torques must balance. Any clockwise torques have to be balanced by counterclockwise torques.